Euclid's Elements, Book 1, Proposition 21. If on one side of a triangle from its ends there be constructed two straight lines meeting within the triangle, the straight line so constructed will be less than the remaining two sides of the triangle, but they will contain a bigger angle. This is, again, one of those ones that's easier to see once we draw it out. So let's take a triangle. Okay, so let this be the base of our triangle. And let's have our triangle. All right, and if we have two lines that are constructed on one line of this triangle, let's just pick this orange line, and these meet within the triangle, like so, what we're saying is that the measure or the length of these, oh boy, the length of these two lines will be less than the length of these two lines, but that it will contain a greater angle. Now, notice what we're not doing is we're not comparing triangles, because if we were, this would be immediately evident. We could immediately say that the triangle in green, right, is less than the triangle in black, because this is clearly a part and this is clearly the whole, and the part is always less than the whole. So we would definitely be able to say right away that the green triangle is less than the black triangle, but we're not saying. We're just trying to compare these two legs of the triangle to these two legs of the triangle. And to do that, we're going to have to use Proposition 20. Okay, so that's our goal, to show that these two legs are bigger than these two legs, but that this angle here is bigger than this angle here. All right, so here are the two things we're trying to prove. Okay, the first thing we're trying to prove is that the black legs are greater than the green legs. And to do that, we're going to create another pair of legs. So let's have some numbers here. Let's call this A, B, C. We'll have this point where they meet here, D. And we're going to extend BD until it intersects AC. And I'm going to give that a different color. We're just going to extend this line until it goes here to E. All right, and I'm going to make another line here. It's actually the exact same line, but I'm just going to have it be a different color. All right, so what Euclid does is he creates another set of legs, this red set of legs. And what he's going to do is he's going to show that the black legs are greater than the red legs, and the red legs are greater than the green legs. And because of that, we can then conclude that the black legs are greater than the green legs. All right. Well, we might call these inverted chevron, or we'll call it a TP. All right. So the black TP, which is made up of BAC, is greater than the red TP, which is BEC, which is going to be greater than the green TP, which is BDC. So if you keep that in mind, that's our goal. And remember, our second goal is then to prove that this angle, we'll call this angle 1, is greater than this angle, which we'll call angle 3. So we're going to prove angle 1 is greater in green than angle 3 in black. All right, so we're going to use Prop 20 a couple of times. And Prop 20 is the prop that says in a triangle, any two sides taken together in any manner are always greater than the third side. So we're going to talk about two different triangles. The first triangle we're going to look at here is this triangle here. All right, so in triangle BAE, we can see that this leg, BA, plus AE, has to be greater than the third leg, right? Any two legs, leg 1, leg 2, has to be greater than the third leg or the third side. So that has to be greater than EB, which I'm going to keep color-coded over here because it's this red line. Well, let's add then, we got BA and AE, let's add EC to the rest of this. So let's add EC to this side, and we're going to add EC to this side. But I'm going to add, just to keep it straight, the red line, which is also EC. So if we add BAAE EC, you should see that we get BAAC, which is our black legs. And if we add BE and EC, we're going to get, okay, so if we have BEEC, we're going to get our red legs. Well, this was greater than this, and we added equals to unequals. Therefore, it preserves our inequality. Therefore, this is greater than this. Right? So that's our first step. We have that the black legs are greater than the red legs. The black TP is greater than the red TP. Now we just need to do the same thing again with a different triangle. In this case, we're going to use this triangle. I'll put it in red, perhaps. I don't know if that helps. We're going to use this triangle. All right. So the second thing we're going to do is in triangle ECD. Okay, again using Prop 20, we know that any two sides, so DE and EC, we know that DE and EC, those are two sides, they have to be greater than the third side, which is DC. So DEEC is greater than CD or DC. And we can now, let's add this remainder. Oh, DC is going to be in green. Let's keep this color coded. DC. All right, so let's add to this and to this, let's add this remainder BD. So we're going to add BD to this side. And we're going to add BD, but the green part, right, is the same. Oh, sorry. And it's going to preserve our inequality. We're adding equals to unequals, and so it's going to preserve our inequality. Well, if we take DE, EC, and BD together, right, we're going to get BE and EC, which again is just simply our red legs, right? This is our red TP. And that's going to be greater than the combination of DC and DB, right? Which is, this is simply our green legs, right? Our green TP. And therefore the red TP is bigger than the green TP. Well, now we have all the parts that we need, right? We know that the black legs are greater than the red legs, and the red legs are greater than the green legs. Therefore, right, we can conclude that the black legs are greater than the green legs through this middle term. Right? So that's the first thing. We've now proven that this is greater than this. And that's the first thing we're trying to prove. Now it's just left for us to prove that this angle, the angle contained by the lesser legs, contains a greater angle than the angle contained by the greater legs. So again, we're going to use a common triangle. So we're going to look at this triangle here in red, and let's look at angle 1 here, and let's look at another angle here that we'll call angle 2. So here's angle 2. Now you should be able to see that in this triangle, DEC, and we're looking at this triangle, DE has been extended, and therefore this angle here, in angle 1 is the exterior angle. And we know from proposition 16, so here we're doing the third point here, step 3, we know that in triangle DEC, that angle 1, we'll keep them color-coded here, angle 1, the exterior angle, has to be greater than either of the opposite interior angles, which would be this angle here or this angle here. So in this case, angle 1 has to be greater than angle 2. This is Prop 16 of Book 1. It tells us the exterior angle is always greater than either of the two opposite interior angles. So 1 is greater than 2. Well, now look at this triangle. In this triangle, triangle ABE, angle 2 is the line extended, and this angle 2 is the exterior angle. So exterior angle 2 is greater than either of the opposite interior angles. And so angle 2 has to be greater than angle 3. Again, Prop 16. So in this triangle, 1 is the exterior angle, it's greater than 2. In this triangle, 2 is the exterior angle greater than 3. Well, if 1 is greater than 2 and 2 is greater than 3, right, then we can conclude just as we did up here, right, if 1 is greater than 2 and 2 is greater than 3, therefore we can conclude that angle 1 is greater than angle 3. And that's the second thing that we're meant to prove. Therefore, if on one side of a triangle from its ends, if two lines are constructed on that line meeting inside the triangle, those two lines will be less than the original lines, but they will contain a greater angle. And since we have proven that, we can conclude QED.